everyone. Thank you for joining us. I know it's the session after lunch, so we're doubly grateful you're here. My name is Sourabh Shirhatti. I'm a product manager at Uber, joined by my colleague.
Matas and Rastenis, senior software engineer at Uber.
And we're here to talk to you about our experience building agentic systems with Visual Studio Code at Uber. Hopefully most of you have heard about Uber. Maybe some of you even took an Uber here today. We do 30 million trips a day. We operate in over 10,000 cities, and it takes tens of millions of lines of code to power that. So we know we have our own problems with that, a code base of that size, and we're also constantly adding new code. So we built this tool to solve a problem for us, specifically around authoring tests, and we'll get into it today. So it's a packed agenda, but for that post-lunch rush, we'll give you a live demo. So pray to the demo gods here. And we do have time for questions, so please hit us with your questions, and we'll also stick around later if there are more questions. There's one more thing I want to talk about. We're super excited by all the announcements around Copilot extensibility. I think the Copilot multiple file edit, we saw for the first time yesterday, so we obviously haven't had time in the past 24 hours to go update our product and make use of all those features, but if you're not, we're still super buoyed by the direction of the extensibility API, and we think we have the right abstractions in place, so you should be able to extrapolate from what we're showing you today. And so with that, Matas, kick us off.
Sure. So let's explore the problem. What are we solving here? So we all know that unit tests are extremely important while developing code. But the problem that we're solving is that writing unit tests is both hard on the engineer, and it is difficult to make them complete enough and adhere to all of your company-specific conventions that you may not even know about while writing them. In addition, maintenance after you've written the test is also often a challenge. If you want a super complete suite, you'll have to have the maintenance burden come along with that. We measured the number of steps that it takes for an engineer to write a unit test at Uber, and we came up with a number of 29 steps. Now, admittedly, some of those steps are trivial, like creating a test file, but it still adds up in the long run to a lot of toil that takes away from the productivity of the engineer itself. So just a quick show of hands, who really enjoys writing unit tests every day?
I know I don't.
One hand, two hands. Let the record show 2 hands, 3 hands. Right, so that's exactly the problem we're trying to solve here, is give you a tool to speed that process up and to help you arrive at better unit tests in the end. And that's what we built the tool for. Now, you might be skeptical, and we were skeptical as well of LLM-generated unit tests. But we've put in a lot of work to make sure that the quality of those tests are up to snuff. And hopefully by the end of this presentation, you'll be a bit more convinced as well. So before we get into the tool, I just wanted to give a preface of how we got here. So the initial sort of set of tooling that we had for writing unit tests were sort of prompt presets that you could use to generate unit tests that had Uber conventions and some other stuff. Now, that's all well and good, but in practice, they weren't that usable. They were clunky. You had to read the docs, get the prompts, put them in, generate your tests, then splice them in yourself, test them, and sort of iterate. And it ended effect of people just not using them very often. So that's what we're iterating on here. We got this product out called AutoCover, and we're still building it. And the experience is, we were lucky that at around the same time we were discovering this issue with our current testing generation system, we discovered that we have the capability to plug up to Copilot and do a chat participant. So if you can see on the screen, the paradigm of use is you invoke a chat participant, and you get tests at the end after some time, after some internal looping. So in this case, it's a nice little table test, complete and with edge cases and everything. So yeah, that's our experience. We're going to get into how it works. This is just a flash preview. But to kick us off, Sourabh, why don't you take us through what agentic systems are?
Awesome. Yeah, so you might have heard the term agentic system maybe before our talk today as well. It's not complex jargon. It's just an agentic system is a system comprised of multiple steps, and each of those steps performs a very specific task, right? And so we're just chaining them together, allowing these agents to collaborate with each other and just specialize and focus on the problem that they're best suited to solve. And if there's one takeaway you take from this talk today, that should be it. If you take the output of a probabilistic model, right, and you add guardrails that you get from deterministic tools, like a compiler, which will give you errors, or a linter, which will give you warnings, if you add that in and add it as context to subsequent generations, the overall precision and quality of the output for your system is going to greatly increase. Right? So asking an LLM to, hey, just fix my test is going to be hard. It may not know what's going on. But if you say, fix my test, and here are all the compilation errors I saw while trying to build this test, or here are the test runner logs from when the test failed, and here's the source code that I was trying to cover with my test, it's going to do a whole lot of a better job. So that's what we're going to do. We're going to use these agentic principles, break the problem down, and then feed that into a model to get better results. So at a high level, what did we do? We took this large, somewhat nebulous problem, like, how do I write a test? And we broke it down into like smaller, solvable, and tractable problems. And that's very similar to what a human would do. If you were tasked with writing a unit test, you do exactly that. You say, let me dive into the code base, kind of see how it works, figure out what the state of coverage is right now, maybe try writing a test, compile it, feed all that back into the system. And so what we're going to do is walk you through each one of those. I just, at a high level, spoke about a couple of systems. So Matas is going to kick us off. He's going to introduce an example. It's not just a hello world code. It's a little more complex than that, but it is indicative of something that you may see in your code base. And he's going to just motivate what that library does so that you have context for subsequent slides when you see code snippets on the screen. So Matas, why don't you introduce the demo?
Right. So, before we explore how AutoCover works, we want to introduce a sort of a bounded example, as Sourabh just mentioned. So this is, a piece of source code. It contains a sort of functionality to parse resource identifiers, so think like a URI. We can take in a string and output like an identifier object that we can use to route, or you can turn it back into a string again if you want. Now, this is, as Sourabh mentioned, you can find this in a util folder in prod. Like I've found many a simpler piece of code. But the thing is, we want a nice little bounded example so we can iterate on it through the presentation. We have one Go file and no existing tests at all. And we don't know what the coverage status is. Now, for this example, because we have no test files at all, you can infer that we have no coverage. But as soon as you add at least one test case somewhere that could, touch this code, you lose that ability to infer that, and you have to calculate, your coverage. So right now, we don't know anything. And so that's where AutoCover starts. We drop it into a code base. We give it a target, a set of files or a file. And it starts with the first agent, which is the preparer. And what it does is, its purpose is to create as good as an environment as possible for the rest of the agents to operate properly. So it does a setup step to, for example, set up the file, create the file if needed, scaffold out the file. For some languages, you need a specific structure for the test suite to be in. You need, in addition, you need to collect context, as much of it as possible. So we get surrounding files, we get summaries of imports as well. So like a whole bunch of context that we can use to more accurately generate tests that are of good quality. And then we do some other setup. For example, if you need mocks and you need to pre-generate them, we do that here as well, so that in the subsequent steps, we don't trip on these simple things that we could prepare in advance. So yeah, that's prepare.
Yeah, and so everything Matas mentioned thus far can be done deterministically, right? And this is something we'll keep referring as we go through different nodes in the system. Some do not require a model at all, right? They're suited to solve a task using existing techniques, but when we look at different nodes in the system, some of them will invoke a model.
Yeah, absolutely. So now that we have everything prepared, we can go on to the generator. And the generator is our first probabilistic agent. So we are using all of the context that we just collected through the preparer, all of the intel, and we move on to the generator. Now, what it does is it takes all of that intel, it takes the target area, right? So we know which lines are uncovered, and it generates some test cases for it. And those test cases are candidate. That is a key word because on the right-hand side, you see some examples here of test cases that we have, and they're sort of individual. You wouldn't really land them. They, could potentially be put in a table test if you prefer those, and most sort of convention sets prefer table tests, right? But why we do this is we want to have atomic units to test and sort of deterministically, check against deterministic, so build tooling, coverage tooling. And this makes it easier. And we'll come back to refactoring these test cases later. Now, yeah, so we just call in a prompt. We get back a big response. We parse out, the code, and then anything else that you might need for the test case. So think imports. For certain testing frameworks, you may need setup and teardown sequences that you need for each specific test case. So all of that we get in the initial phase, package it up and put it in shared memory for other agents to use.
And this is like the /test command in Copilot if you use today. This is the crux of generate me the test, and everything else around it is the machinery to aid and produce better results. And if like the eagle-eyed among you notice one of these tests doesn't pass, fear not. That does happen, right? Like you've had that happen, Copilot generated a test that didn't work, but that's why we have all the other steps that we're gonna get to that's hopefully gonna fix it, and we'll have a passing test by the end of it.
Yep. So then we move on to the executor. Now this is our first deterministic agent that does a lot of work to make sure that we know whether the test cases are initially good or not. So as we have an example of these two test cases that we just generated. We take them, we splice them into the test file, we run a bunch of tooling to make sure that any other dependencies that need to be imported can be imported, right? So we may need to regenerate build files and do other stuff, deduplicated imports, a lot of things that make sure that the file is syntactically correct. And then we try them out one by one. So we sort of do a test case by test case trial. And if you can see for our two example test cases, we had one of them that passed, and it resulted in a 13% coverage rate, which is great. That's what we want. And the second one has a field called version P, which doesn't exist in the identifier struct definition. So it failed to build. And we would take this feedback and include it in the shared memory for future agents to use. Yeah.
And even though this is deterministic, that doesn't make it easy, right? Like the challenges we found while building this out is you have to have knowledge of all the languages and frameworks at your organization. Like if you've ever tried to build code or like contribute to another team in your company and they're like, oh, well, you had to set this environment variable in this build flag and only then can you build it. Like this tool has to have knowledge of all that. So there's also like a preparedness in the organization where you consolidate on your build system. You make sure people don't use like these bespoke build processes outside the build system to make it work. So we keep finding that even the current abstraction we have for executor is still not sufficient. So we keep adding more hooks, more like event-based entry points to support all the various languages and frameworks that we have.
Yeah, absolutely. And then what we do with the results is we move on to another probabilistic step, which is the fixer. Now, we have tried these two test cases that I just showed, and we had one that failed. So fixer has a very specific purpose, and that's what we found of like scoping in the responsibility area of an agent helps it focus in a lot more and output way better results. In addition, we send in parallel prompts or parallel calls to the LLM for each test case. So we give them a bit more context window to hopefully allow the LLM to elaborate a bit more. And we can do this because everything is built in LangGraph. It's a nice abstraction that we can do these types of things in. And then, right, so we got back a response, right? The second test case was sent in, and based on the error that was provided by the executor, it actually fixed it by removing version P and adding version. So this is a very contrived example that was just manufactured, basically. But you can imagine a much more complex scenario where, let's say you're calling a function that you have 4 parameters in, well, the function takes in 3. You don't know the exact definition, and you can derive that from the compilation error. So fixer addresses those types of issues, and it helps a lot of test cases that in the initial shot don't pass to actually work properly. Yeah.
And now this is where you start seeing, this isn't just like 4 sequential functions we're calling, right? This is a complex state machine. Like fixer in this case is able to collaborate with the executor and say, hey, mark this candidate test case for execution again. Because just because we attempted to fix it with the model, we don't know that the fix is valid. So we have to run it back through the system and fix it. And sometimes it takes multiple iterations because the model doesn't get it right in the first time. But this is, this is where you'll see it's not just linear flow through the system. It's a state machine that you have to manage.
Yep, absolutely. And so let's imagine, we've had 10 or 20 test cases. We've sort of fixed up the ones that can be fixed up, and now they pass. And now we're at the point where, like, okay, we have these candidates. We want to start preparing them to like show them to the user. So what we do is we pass them through the refactor agent. And what the refactor has is, it has sort of a directive to, first of all, look at Uber best conventions. We have a big formulaic list for that. By language, it's split up pretty modular and nice. And to make sure we adhere to those. And then in addition, combine the test cases into larger table tests now. So we're finished with sort of the initial experimentation of atomic single test cases. We're gonna prepare them to sort of be almost productionizable. So that's what we get out of the refactor.
And what we learned here is the abstraction that we use for an agent has to support composability of multiple sub-agents. Right, and let me elaborate on that. So Matas explained we have this one sub-agent in play today, which reduces verbosity, right? It looks at similar test cases, combines them into a test case. But there are other tools you may want to invoke. You have things like, syntax tree-based linters, right? Like some of you folks may be using Go format, you may be using like rough or black in Python. We want to integrate those too, but for the ability to integrate multiple different types of tooling, you need to have that composability of sub-agents. So that's also what we learned while building out refactor.
Right, and so now, we've refactored these two previous test cases into this example here on the right, which is a single table test, which is way, way better. And now we're on to the validator step, which this is our QA component. Here is where we sort of step back and say, okay, is the test case that we generated, does it actually assert anything, and does it assert the right things? We want to make sure that whatever test we output, they're not just blindly executing the code and like not asserting anything. That's a big worry for all engineers. It's like, well, are these tests actually doing the right thing? So validator is what we have for that. And as Sourabh mentioned, we have or agents that have multiple sub-agents. And this is the first one when we actually have multiple ones already. So the first one is a simple deterministic sub-agent, which is a mechanical check to check if we have an assertion at all. That's pretty simple. If you don't have an assertion statement anywhere, you can probably pretty clearly invalidate that test case and try again. The second sub-agent is a probabilistic sub-agent, which is the LLM critic. So if you remember, I spoke about the large list of conventions that we had, and we passed that in already, but we want to validate that these tests actually adhere to those. So validator, the LLM critic subcomponent goes through those conventions and actually maps back, and if it finds inconsistencies, it will flag those up and attach them as feedback. So think, for example, if you have mutexes in your code, if you just generate the test for like, add to list, remove from list, delete from list, or whatever, you'll have 100% coverage, but you haven't actually tested the concurrency functionality. So you need to add concurrency tests to that. So yeah, and then the third subcomponent is the mutation tester. And I'll talk about that in the next slide.
Yeah, I just want to talk about what we learned while building this before we get to mutation testing. So the first we learned is we have to take a multi-shot approach to adherence, right? Even though during the generate phase or the refactor phase, we tell a model, hey, please author a test or refactor a test using this style guide, which we may include in the prompt. The model doesn't always comply, right? Which is why we run it through a model again to validate whether it actually did what we said. And I'm super excited about the model selector support in Copilot, because now we can even pit models against each other. Did a model do what the earlier model was asked to do?
Yep.
So that's the multi-shot approach to adherence. The second thing I want to talk about we learned is the agent abstraction also needs to account for the fact that sometimes you need a seed control back to the human. It cannot infer what's going on. Like, let's say you don't have sufficient doc comments or your code is written in an obtuse way. Just like a human would struggle to understand what that code does, a model may do so as well. So we're also looking to add more of these interaction paradigms and light up the right UI in the IDE so that the model can come back and ask you, hey, I didn't understand what was quite going on here. Can you give me a little more context so I can try and write a better test? So that's something we're still going to build out. We learned, but we don't have yet.
Right. So let's get back. Oh, this is an example, sorry. So we had a table test, right? And an example for the validator for what it could tag onto the table test is, it sees that, for example, we're missing edge cases in this case. So it even suggested 3 edge cases that we should be adding, and a lot of them are, either it's like a Unicode symbol and see if it's parsed, or if it's an empty identifier, things that we actually didn't check for. So we're, iterating on and expanding on these test cases. So after we get this feedback bundle and pass it back to the fixer and then the executor, we arrive at a new iteration of this test case. So now we have, a more fuller, sort of from 3 to 6 sub-test cases that cover much more of what the source is supposed to be doing, and the edge cases that we should be covering. So moving on to the mutation testing subcomponent. So we're really excited about this because this is sort of the first component where we go beyond what a human would ordinarily do while creating unit tests, and we automate all of that away to arrive at way better quality unit tests in the end. So before I dive into this, let's just explain what a mutant is for anyone who might not be aware. Let's say you have your source code and some test suite, and we want to make a change to the source code that is unintended, and see, not the test code, the source code, and see if your test suite actually catches that unintended change, right? And if it doesn't, then you might be in trouble. It may be something like, a bug was introduced at some point, and if your test suite doesn't catch it, it's likely that you need to expand your test suites for that. So here, there's an example here on the slide where we are parsing a string, and we check for that the string is of v2 format, so it starts with v2. And then the mutant changes it so that instead of calling parse v2, we call parse v1. So that's a pretty breaking change. You will be parsing v2 strings as if they were v1 strings. And if your test suite doesn't catch that, that's a big problem. You need to get that addressed. Another example is, this is in parse v1, so it's in one of those subfunctions. And you have an invalid format, so you have like no segments or whatnot. And we usually would return an error. But the mutant changes it so that we just swallow the error and don't return it at all. Now, that's also a contract breaking change. If you depend on that error, you no longer will get it. So what we do with these mutants is any ones that pass, we bundle up into feedback and go through the loop again to try to add more cases to sort of address the shortcomings that we found.
Yeah, and harping back to the deterministic and model-based approaches, the generation of mutants can be done both ways, right? We can say, hey, parse the syntax tree and invert every if condition. That's a deterministic way of introducing a mutant. Or we can do a probabilistic way. You can say, hey, LLM, please introduce a subtle bug in my function and then run the test. So that's where the composability of LLM-driven and deterministic approaches comes back. We spoke about a lot of these nodes in the system. This is a complex state machine, and we talk about how the candidate code travels through each one of these states. And all of this happens unbeknownst to the user, right? If you think back to what Mata showed in the beginning, you invoke the model, and then you wait a bit, and tests just stream into your editor, and you're potentially good to go. But you folks are lucky. You're not our end developers, so we're going to give you a peek behind the curtains. Matas is going to hop over to his computer, and we're going to look at a live demo soon. And what he's going to do is he's going to stop the execution of AutoCover at some of these pre-selected states, and we'll show you what the model or the system was thinking and what the feedback is before it goes in for a second or third iteration.
Yep. So I think let's get into the demo then. So this right here is the exact sample project that we had, right? We have the parse and parse v1, parse v2, and then a stringification tool. We don't know anything about the coverage. We see that we have no tests. Let's pop over to our test explorer panel and actually run our test suite, which is non-existent. And we go back, and so we see that if we move over to the bottom here, we have 0% coverage, so no tests. And if we look at the source code itself, we can see everything is highlighted in red because we haven't actually tested it.
And then, right off the bat, I see not every line is marked in red. Why is that?
Right. So we don't have every single line marked as uncovered because some of these are just declarations. For example, this is a struct definition. We don't actually need to cover this code, right? And this is the first place where we sort of step ahead, just a blind approach of, send the file into an LLM and just get tests out, because we actually know exactly what to target. We know that we have multiple functions that need targeting, but this is not really an interesting target for us. So we scope in, and we can get better results that way.
So this is already an incremental improvement, right? Rather than selecting the entire file and saying, generate test for it, you say, hey, lines 18 through 26, I want to cover that function, generate a test for that.
Yep, absolutely.
Okay, so we know we don't have tests. Can we start the process of generating tests?
Right, let's do that. So we move over to the chat panel, right? We have Copilot, good old Copilot, and we can invoke AutoCover. So we do @AutoCover/start. Now, this will do a bunch of stuff in the background, and it invokes the whole chain that I just showed, and it opens up a new, the test file for us automatically, which is super cool. Right now, it is a fire and forget, so you invoke it, and you sort of look at what it does, and you get the tests out. But in the future, we want to be able to call back, and if something is continuously failing, or if we're not sure if we are moving in the right direction, or if we have everything covered that you want, all the scenarios, we want to be able to, the user to be able to chat again with Copilot. So like go back to the chat, add some, ask some more questions, make some more corrections.
And like, fear not if you can't make sense of the log spew. It isn't intended for people to consume. So we are going to hop over into a sort of a debug viewer that we built to show you what the intermediate state is. So Matas, what's the first state in the graph that you're going to stop us at and show the intermediate?
Right, so let's move into our Explorer that we have. And so we have, the first initial state that we have here will be after the initial generation. So we've generated these test cases. We may have some reloads here because it's still outputting new state dumps, which is great. And so we have the initial tests, the candidate tests that have been generated in the generator component. And I'll just introduce this flow here. So we have the test configuration panel, which shows us which node we're currently in. We can select the text function, and we see how many tests we've generated, how many we think will be needed to cover the code. And then if I select a function, we can take a look at the imports. In the context of Go, we really only need imports right now. We don't have teardown setup, whatever. We may add that later if needed. But right now, imports and the code itself. As you can see, the test case state is unknown. We actually haven't even run the code yet. So we're just, we generated something. We don't know if it's any good, if it builds, if it passes. And yeah, we have this. As you can see, it already actually generated a table test, or future, or newer generations already start with a pretty good format. So it makes it easier for refactor to just merge these together. It has to do less work. And if we scroll down a bit more, we have the feedback section, which doesn't have anything because we just generated the test case. We have no idea if it passes or builds. Right.
So I think there are a couple interesting things, right? If we look at the imports, it was important to split up the imports because sometimes you have to interact with the build system. You may have to like run your package manager to pull in new dependencies. That's why we wanted to split it up. And so, Matas, why don't you show us the next step? I think you're going to show us after executor, right?
Right. So the next one, let's go to our next state dump. So we're exiting the initial run of executor now. And we have our test functions here, the same ones. And if we scroll down, nothing really has changed except for that we have a new test case state. So in this case, we've validated that whatever we generated actually builds, the test pass, and the coverage has, so the coverage was raised. And it's important to note that right now we have coverage raised, but we'll be expanding this with more metrics such as survival or mutation testing mutant survival rate, for example, and branch coverage. So we're not sort of keying in on that specific metric too much, but this is what we have right now. And if you scroll down, we don't have any feedback. That's because everything passed. Everything seems okay. Like the test case, that's the executor's job, is just do that one thing, just execute, and return us this feedback of, yeah, it did raise coverage.
So in this case, your test actually passed and raised coverage. What would have happened if the test failed? What would we see here?
Right, so if we had a test failure, we would actually see a different state. We would see, build our test failure here, and then scrolling down, we would get feedback, and the feedback would be either the output from the test runner or from the build system, saying either this is an invalid field, as we saw before, or that this doesn't quite pass. And sometimes that's really good feedback because the test not passing may indicate that there's an issue with the source, and then we can't really do anything. We may want to reach out to the user for that, and that's what we're going to work on next.
So we've simplified it. We made feedback just a simple textual field, and you'll see that as we go through the system. But you can have complex structured data that you attach that then you pass back to the model for subsequent generation phases. So can we look at the next phase? I think we're going to look at post-validator, right?
Right, so now we have, the next state is after the initial validation step. So now we pass forward a few steps, and we're at validation. And if we select a test function, we see that the new test state is that validation failed. So there was something wrong with the test case. And we don't have any changes yet to the test case, but in the feedback section, we see that we have some feedback. It is not addressed, which is right, because we just generated it. And if we scroll down, we can see a whole host of information about which rule exactly out of our big compiled rule list we have violated. and then a description, and then it even gives us a prompt for, in this case, it gives us a couple of examples. So for example, we're missing edge cases. That's the main problem. And it's asking AutoCover or Fixer to add like a couple edge cases to fix for identifiers with empty parts. How do those stringify out? So it should be an empty and v2 in this case. And yeah, so that's the feedback. We attach it and go back through the loop.
And the interesting thing here is you can see we're not just overfitting for number of lines covered. We have other heuristics, like catching edge cases is something you want your test to do. Sometimes you'll get feedback from validator talking about focus on readability or use like named parameters so people can understand what you're doing. And we're going to continue to like evolve those heuristics. Matas mentioned some around make sure mutant survival rate improves.
And so mutation testing results would also show up here. If you had a mutation testing, surviving mutant, surviving bug, you would see it show up in this feedback.
Okay, what's the last state we're going to see?
So the very last state is we got this feedback, bundle it, we passed it back through the loop. Fixer had a shot at it, executor verified it works. And so if we go next and we pick the same function, we're at the exit of AutoCover. So this is what we actually output. And if we scroll down, this test case state is back to coverage raised. So we're still clear. Sometimes the fixer makes the test case not build, so we want to avoid outputting broken code in the end, right? So we go a few more loops through. And if we scroll down, we actually see that the table test has been expanded with the exact examples that were suggested, right? So we're adding new edge cases and iterating on this test case as it goes through the system. So that's a really cool property, and you can adjust how many times it goes through and sort of iterate that way. And the feedback has been addressed now. So it's flagged as, yes, I've looked at it and addressed it.
Okay, so folks aren't going to be interacting with this viewer, so let's maybe jump back into what a user of AutoCover might see.
Right, so what you would see is, the empty test file that we just had is now populated with a bunch of tests. And we have all of these tests here and all of the expansions with the new edge cases that we have added. And I think
were we successful? Did we raise coverage?
Yeah, so any guesses as to what the coverage is now for the whole file? 90. Okay, one guess 90. Let's see, 100% I think I heard. Let's try to run our coverage check again.
Fingers crossed.
I'll have to just rediscover the test. Right, and then if we look down here, we actually have the coverage at 100%. So that's really cool. We're able to just sit back and cover this whole file.
Yeah, and then can we look at the source file, just see the annotation? Yeah.
Right, so, and now we have the highlighted parts that are covered in green. We'll have potentially other indicators that are like, hey, we've tested this branch, or that we've covered this piece of code with 2 test cases, because that's a new metric that we're experimenting with. So how many cases cover the same code to have redundancy? Yeah.
We're not always going to hit 100% coverage, right? Like it depends on whether we can discover intent, whether we can generate tests. But in terms of just talking about keystroke safe, right? Like 15 characters typed to invoke AutoCover, and it generated about 110 source lines of code. Mm-hmm. It's pretty effective. Like I use it, a bunch of engineers at Uber use it. So hopefully, we sold you on this idea, this pattern.
Right. And yeah, you would show up if you have some missing coverage at this point. It's more likely than not the code is too complex, which is okay. Or we have like a bug or something in the source, which we don't want to cover. We don't want to be like, oh yeah, forget about it. So anyway, that's about it for the demo.
Yeah, let's maybe hop back into slides. Just a few things we want to do before we next. Now that we've proven it out with Go, we obviously want to expand to other languages. I spoke about some of the challenges to support every single framework, every single build system, but we're super bullish. I think Java and Python support are coming along really well, and we hope to productionize that at Uber. Second thing we want to do is what we call standalone mode. Some of AI adoption is a technical problem, some of it is a social problem, right? You might have encountered some fellow developers who are not ready to hand over the reins to AI, like, I don't want to trust this generation. That's okay. We're still adding value with these agents that make sense to consume piecemeal. You may not want AutoCover to write your test, but you may want the same validation logic. Like, why wait till you submit a PR to get that feedback, right? Why not get it earlier in the cycle? So we're going to allow you to invoke that, get that feedback earlier on. Also, things like mutation testing. It's actually kind of tedious and annoying to do. If you can just invoke a tool that'll do it for you, why not? People, even AI skeptics would use it. So that's what we're trying to do. We're trying to reach out to everyone in the organization. And then the third thing I wanted to talk about is we're sort of adding this consulter mechanism, right? So we spoke about how agents sometimes need to cede control back to the humans. So we need to integrate with like native UI or UX in your IDE where you can prompt a user for what needs to happen. Maybe that's through a chat box. Maybe it's through go add doc comments in your code. We need to figure out the right paradigms. I think some of the stuff that came out of the announcements yesterday is super cool. We're going to integrate into that. But I also want to point out there are places in the IDE outside of the chat that it makes sense to integrate. We already showed you for coverage, we were using like highlighting, you saw the red and green. We're also looking in things like gutter indicators, code lengths, right? Like you can have a code length over a function and says, hey, generate me a test for just this function. So we're going to look at other entry points too, so people organically discover this, so that they don't have to like know the right incantation or, we know people don't RTFM. So we're going to add that in.